Welcome to the presentation about GTOs and thyristors as core components in megawatt charging applications, as well as refurbishment for mining and railcar equipment. So commercial vehicles charging, electric commercial vehicle charging takes place in a combination of charging voltage and charging current. Taking a look at today's 900 volt cutoff and 500 amps for passenger cars, there's a certain region given by maximum voltage, maximum current, and a power limited to 350 kilowatts. In commercial vehicle, the high power charging standard is extended to 1500 volts and up to 3000 amps. The area here is given by the cutoff voltage, the cutoff current, the maximum current, and the by the way area is because there's a maximum power limit introduced of 2.2 megawatts today, potentially growing to 4.5 megawatt in the near future. So classical approaches how to build this are based on having a three-phase supply with typically 400 volts in Europe, which is rectified. Then the DC link is converted into a high-frequency AC. The high frequency is demanded to drive an isolating transformer, so the galvanic isolation becomes part of the scheme. And then the high-frequency AC is rectified and given to a battery in form of DC. All this is packed into one power module or one subunit, and then it forms something like a 60, potentially 80 or 100 kilowatt subsystem. Hopefully, is used to charge the vehicle, and the sum of those subsystems is stacked and then provides high power levels to a single battery. In this case, each of the system takes three-phase 400 volts and converts it to DC on a power level anywhere between 16 and 100 kilowatts as of today. Those subunits are stacked, and that upgrades the power level. Potentially, it achieves redundancy as well in case of failure. Detrimental is the high number of interconnections that is needed, and additionally, there is one isolation entity in each of the modules, which may not be the best approach here. Similarities between charging and electrolysis can be considered. So both the topologies share that you need to apply megawatts of power in DC with a highly precisely controlled current. B12C thyristor approach is used in electrolysis a lot, and the schematic shows that a special design transformer supplies three-phase power to two independent B6 bridges, forming the B12 bridge in sum. LC filters are added, and then a series connection of electrolysis cells is what is driven by this application. Electrolysis cells are single cells with less than 2 volts for each cell. So potentially the very same system is a great idea to drive a string of battery cells. If based on thyristors, efficiency becomes a real good factor. So even with a classic thyristor in place, the losses in this thyristor at 1000 amp of throughput, the whole bridge only creates 2 kilowatts of losses, but achieves a megawatt of throughput. This leads to an efficiency in the regime of 99.8% at a throughput of 2.2 megawatts. Sounds too good to be true? It's not. So taking a look at the thyristor and the efficiency issue. The thyristor is a nonlinear piece of hardware. So building a B6 or B12 bridge from a thyristor, the forward voltage on a 500 amp forward current is in the regime of 1 volt. But because due to the nonlinearities, even at twice the current, 1000 amp, the forward voltage only grows by 150 millivolts. So this, let's assume an estimation, leads to about 2.2 kilowatt of losses in a B6 bridge. Overall losses, because there's 2 bridges involved, is 4.4 kilowatts, which leads to an overall efficiency of 99.8%. So how good is this guesstimation? Well, supported by simulation. The thyristor losses turn out to be 384 watts per thyristor or 2,300 watts per bridge. So the guesstimate is pretty accurate if the simulation is considered precise. So with silicon carbide MOSFETs and 2 energy conversion stages, very often a claim is we can achieve 97% in-to-out efficiency. The thyristor approach achieves 99.8, and those 2% really matters. Besides that, Size matters. It's all about how many resources are needed to build something. Resources per kilowatt installed becomes a dominating factor. And a stack, as in this picture, that handles the B12C setup is just 90 by 70 by 80 centimeters in width. So comparing this to a classical approach, here is the drawn to the scale picture. With 97% efficiency and 2 megawatt of throughput, something like 60 kilowatts of losses need to be dissipated, which demands quite a huge chiller, represented by the blue block. This chiller can transfer 70 kilowatt of thermal power, but it demands 20 kilowatt of electricity to do so. The sum of devices in 60 kilowatts to support a more than 2 megawatt unit means there's 42 units to be parallel, which leads to 84 connections for tubes and the same number of screws to do the electric connection. In contrast, a single unit in one stack formed from 2 B6 topologies is all it needs to convert the power. And on scale, the silicon carbide-based solution of 42 units would consume as much as 6 cubic meters of space, while the thyristor-based approach only takes 10% of that. The factor for resources per kilowatt installed is massively better in the thyristor approach. Another area where thyristors and GTOs are still in use is refurbishment. Those expensive mining trucks get new cabinets to remain in service. Very similarly, the ICE-1 train of the German railway, for example, commissioned in the early 1990s, is refurbished to be in service for another 25 years, achieving 50 years in service afterwards. So here, refurbishment is the way to keep expensive heavy-duty equipment running. Upgrading is not always an option. Potentially, changing from one technology to another will void your permit of operation, which leads to a high effort in requalification. And that's why refurbishment with the initial components is demanded. There's a rule of thumb in heavy-duty equipment. As long as refurbishment is less than 50% of the value of the equipment, go for it. Do refurbishment. So here, for the next decades, thyristors and GTOs will remain in the field and Little Fuse is up to serve you with proper components. Thanks for your attention. And if you have any questions, drop them into my email box and I'll get you an answer. Promised. Have a good time. See you soon.